Good morning students, this is Latif sir. Today in this video, I'll discuss about shape of different orbitals, shapes of orbitals and how to write electronic configuration. In the previous video, while discussing about different types of quantum number, I have told that electron in an atom can revolve around the nucleus in different circular paths or in different energy levels, which are known as shells or orbit. And each orbits are represented by principal quantum number small n, and under each energy level or each cell there are some subcell, and subcells are represented by azimuthal quantum number small l. Okay, and under each subcell there are some orbitals which are represented by magnetic quantum number ml. Okay, and today I'll discuss about the shapes of different orbitals. So first see the shape of s orbital. For s orbital, you know s orbital is present in s subcell. s orbitals s orbital is present in s subcell, and for s subcell value of azimuthal quantum number ml is 0 and value of magnetic quantum number ml is also 0. Okay, and what is the shape of s orbital? It is the shape of s orbital, it is s orbital has spherical shape. S orbital has spherical shape with uniform electron density along all the three axes. Now see size of different type of s orbitals. This is 1s orbital, 2s orbital and 3s orbital. Size of different s orbitals is in the order 6s orbital is greater than size of 6s orbital is greater than size of 5s orbital is greater than size of 4s orbital is greater than size of 3s orbital is greater than size of 2s orbital is greater than size of 1s orbital. Okay, so this is the first one is size of 1s orbital. This is 1s orbital and this is 2s orbital and this is 3s orbital. As the principal quantum number value of principal quantum number increases, the size of different s orbital also increases. Okay, and you can see there are some empty spaces in 2s orbital and 3s orbital, and these empty spaces are known as node. Okay, so the spherical empty shell for 2s electron is called nodal surface or simply node, and in 2s orbital there is a single node, and in 3s orbital there are two nodes. Okay, and in node or nodal surface electron density is 0 or nil. Now see shape of p orbitals. P orbitals are present in p subcells. P orbitals are present in p subcell, and for p subcell we know that the value of azimuthal quantum number L is equal to 1 and value of magnetic quantum number ml can have three possible values, that is -1, 0, +1. For p orbital, for p subcell value of azimuthal quantum number L is equal to 1 and value of ml is equal to -1, 0, +1. So p subcell has 3 p orbitals. P subcell has 3 p orbitals which are designated as px, py and pz. P subcell has 3 p orbital and which are designated as px, one is px, py and pz. Now see shape of different type of p orbitals. The shape of p orbital is dumbbell shape consisting of two portions known as lobes. So p orbital has two lobes. This is these two lobes, and this is a shape of a d orbital, and the electron density in the nucleus is 0. Okay, and this is known as nodal plane. So the general shape of p orbital is dumbbell consisting of two portions known as lobes. Moreover, there is a plane passing through the nucleus along which the finding of electron density is almost zero or nil, and this plane is known as nodal plane where electron density is zero. I have told that p subshell has three p orbitals which are designated as px, py, and pz depending upon the axis along which they are directed. Now see shape of defined p orbitals, that is shape of px orbital, py orbital, and pz orbital. Okay, px orbital is oriented along x direction. Py orbital is oriented along y axis, and pz orbital oriented along z axis. Okay, so these are three p orbitals, and shape and energy of all these three p orbitals under a particular cell. The energy of this all three energy of all these three p orbitals, that is px, py, and pz, are same, but their orientation in three direction are different. Okay, and that's why these three p orbitals in a particular subcell are known as degenerate orbitals because their energy is same. From the dumbbell picture, it is quite obvious that unlike S subcell, a p orbital, unlike S orbital has no directional nature, directional property, but p orbital is directional in nature. Okay. And now see size of different p orbitals. As the value of principal quantum number increases, size of size of p orbital also increases. Okay, so size of 4p is greater than size of 3p is greater than size of 2p. Now see shape of d orbital. D orbital look like this, and for d orbitals are present in d subcell. For d subcell, value of azimuthal quantum number L is equal to 2. For d orbital, d subcell, value of azimuthal quantum number L is equal to 2. So value of magnetic quantum number ml will be -2 to +2, that is value of ml will be -2 -1 0 +1 +2. So there are 5 possible values of ml for d subcell. That means d subcell has 5 d orbitals, and these d orbitals are designated as dxy, dyz, dxz, dx square y square, and dz square. These are 5 d orbitals. Okay, and energy of this all these 5 d orbitals are equal, but their orientation in space are different, and these 5 d orbitals are known as degenerate because their energy is same. Okay, so this d subcell has 5 d orbitals of equal energy, but their orientations are different. Out of these 5 d orbitals, shape of first 4 d orbitals, that is shape of dxy, dyz, dxz, dx square y square, shape of these 4 d orbitals are similar to each other. Okay, and which is different from the dz squared orbital, and energy of all the 5 d orbitals is same. That's why all the 5 d orbitals are called degenerate orbital because their energy is same. Now you can see different types of d orbitals. This is dxy orbital, dyxz orbitals, dyz orbital, and dx square y square orbital. And this is dz square orbital. You have to remember the shape of different d orbitals. You have to draw in exam also. Okay. Now see, one note is given, number of radial node. Radial node means where electron density is 0. For a particular orbitals, node means it is a space where the electron density is 0 or electron density is nil. Okay, so number of radial node for a particular orbital can be calculated by using the formula n minus l minus 1. Using this formula, you can calculate the number of radial node. Okay, so the formula of calculation of number of radial node for a particular orbital is n minus l minus n l minus l minus 1, where n is principal quantum number, l is azimuthal quantum number. Okay, for example, if you for example, for 3p orbital, what will be the total number of radial node? 3p orbitals. 3p orbitals, for 3p orbitals, value of principal quantum number n is 3, and for p orbital, value of azimuthal quantum number l is 1. So for 3p orbitals, total number of radial node is 3 minus 1, that is 1. Similarly, for 4d orbitals, value of principal quantum number n is equal to 4 value, and for d orbital, value of azimuthal quantum number is 2. So for 4d orbitals, total number of radial node is 4 minus 2 minus 1, that is 1. Okay, so these are the shapes of different orbitals. Now I'll discuss about three basic important principles or rules, and using these rules you can write the electronic configuration of different element. Okay, so first type of rule is Aufbau principle. Aufbau principle, very important principle, and this principle states that in the ground state of the atoms, the orbitals are filled in order of their increasing energies. That means electron will enter into the lower energy orbital first, then in higher energy orbitals. Okay, so according to Aufbau principle, in the ground state of the atoms, the orbitals are filled in order of their increasing energies. In other words, you can say electrons first occupy the lower or lowest energy orbitals available to them, and then enter into higher energy orbitals only after the lower energy orbitals are filled. Okay, so you can also say according to Aufbau principle, electrons first occupy lowest energy orbitals available to them and enter into higher energy orbitals only after the lower energy orbitals are filled. Okay, and the energy order of energy order increasing order of energy of different orbitals is given here. You can see energy, this is the increasing order of energy of different orbitals. Okay, energy of one energy of 1s is less than 2s is less than 2p is less than 3s is less than 3p. Okay, this is the energy order of different orbitals. The order in which the energies of orbital increases, and hence the order in which the orbitals are filled, is as follows. This is the order of increasing order of energy of different orbitals, and in this order electron will enter into the orbitals. First electron will enter in 1s orbitals, then in 2s orbital, then in 2p orbital, after that 3s, 3p, 4s, 3d. Here one point you have to remember that energy of 3d energy of 4s orbital is less than energy of 3d orbital. Okay, you have to remember this point. Energy of 4s orbital is less than energy of 3d orbital, then 4p, 5s, 3d, 5p. So you have to remember this energy order of different orbitals. Okay, and the order may be remembered by using this method. First the energy order is: first electron will enter into 1s orbital, then into 2s orbital, then in 2p 3s orbital, then in 3p 4s orbital, like this. After 4s, then electron will enter into the 3d orbitals: 3d, 4p, 5s, then 4d, 5p, 6s, then 4a, 5d, 6p, 7s, like this. Okay, and this is the increasing order of energy of different orbitals. And how to know which orbital has how to state the energy of different orbitals, that is, which orbital has higher energy, which orbital has lower energy. you have to remember n plus L. Okay, so relative orbitals energies in many electron atoms are given by n plus L rule, where n is principal quantum number, L is azimuthal quantum number. Okay, an orbital of lower n plus L value is at a lower energy level. If an orbital of lower energy value, lower n plus L value, is at a lower energy level, and if two orbitals have same value of n plus L, then the one of lower n is of lower energy. For example, if for two orbitals n plus n, you have to calculate n value of n plus L. Okay, and for if the value of n plus L is low, then the energy of the orbital is low, and if the value of n plus L is high for an orbital, then the energy of the orbital is high. And if two orbital has same value of n plus L, for example 3p and 3p, and for 3p value of n plus L is 3 plus 1, that is 4, and for 4s value of n plus L is 4 plus 0, that is 4. Okay, so 3p and both 3p and 3p and 4s, both 3p and 4s orbital has same value of n plus L, and in such case 3p orbital has lower energy than 4s. In such case you have to see the lower value of principal quantum number. Okay, and using n plus L rule, you can say which orbital has higher energy and which orbital has lower energy. For example 2s and 3p, for 2s n plus L is 2 plus 0, that is 2, and for 3p the n value of n plus L, sum of n plus L is 3 plus 1. For p orbital value of azimuthal quantum number is 1, so 3 plus 1 is 4. So energy of 3p is greater than energy of 2s. Next important principle is Pauli exclusion principle. Very important it is also. Pauli exclusion principle. According to this principle, no two electrons in an atom can have the same set of 4 quantum number. You know, an electron is characterized by 4 quantum number, and according to Pauli exclusion principle, no two electrons in an atom can have the same set of 4 quantum number. For example, if two electrons are present in a same orbital, two electrons in opposite spin, suppose it is present in 2s orbital, then the value of value of all the 4 quantum numbers for both the electrons will be as the both the electrons are present in same orbital, value of principal quantum number, azimuthal quantum number, and magnetic quantum number will be same. Okay, for both the electron values of principal quantum number, azimuthal quantum number, magnetic quantum number will be same, but value of spin quantum number for both the electron will be different. For one electron, value of magnetic quantum spin quantum number will be plus half, and for another electron value of spin quantum number will be minus half. Okay, so three values of three quantum number may be same, but all the 4 quantum numbers will never be equal. Okay, so according to Pauli exclusion principle, no two electrons in an atom can have the same set of 4 quantum number. 2 quantum number may be same, or 3 quantum number may be same, but all the 4 quantum number will not be same. And Pauli exclusion principle can also be stated as only two electrons may exist in the same orbitals, and this electron must have opposite spin. According to Pauli exclusion principle, only two electrons may exist in the same orbitals. Only two electrons can exist in a same orbital with opposite spin. Okay, this is according to Pauli exclusion principle. Now see, here it is given orbitals and electron capacity of first four principal energy level. In principal quantum number F, principal quantum number n is equal to 1, then only S subcell is possible, and in S subcell only one S orbital. So total number of orbitals in first cell is 1. So one orbital can accommodate maximum 2 electrons. In second cell, two S and two P orbitals are present, and total number of orbitals is 4, one s orbital and 3 p orbitals. So total number of orbitals is 4 in second cell. So total number of electron in second cell will be 4 into 2, that is 8, because each orbital can accommodate maximum 2 electrons. And in third energy level, 3s, 3p, 3d or subcell are possible, and you know S subcell has only one s orbital, p subcell has 3 orbitals, and d subcell has 5 orbitals. So in third cell there are total 9 orbitals, and 9 orbital can accommodate 9 into 2, that is 18 electrons. Similarly, in fourth cell, 4s, 4p, 4d and 4f subcell are possible, and p subcell, s subcell has only one orbital, p subcell has 3 orbital, d subcell has 5 orbital, and f subcell has 7 orbitals. So total number of orbitals in f subcell total number of orbital in fourth cell is 16. So total number of electron in fourth cell will be 32. Now see Horn's rule of maximum multiplicity. Horn's rule of maximum multiplicity, it states that pairing of electrons in the orbital belonging to the same subcell does not take place until each orbital belonging to the subcell belonging to that subcell has got one electron each. That is, the orbital will be singly occupied first. Same energy orbitals will be singly occupied first. Then if there are extra electron are present, then the electron will enter into the singly occupied orbital. Okay. So correct orientation of correct electronic configuration, this one is the correct electronic configuration according to Hund's rule. In 1s orbital 2 electron, in 2s orbital 2 electron, in 2p orbital you have to, in 2p subcell has 3 2p orbital, 3 2p orbital, 3 2p subcell has 3 2p orbital, and you have to give 2 electron into different 2p orbital, and this is incorrect orientation, incorrect electronic configuration. You cannot give both the electron in same 2p orbital, because 2p or 2p subcell has 3 p orbitals of same energy. So you have to give 1 by 1 electron in different p orbitals. This is according to Hund's rule. Pairing of electrons in orbitals belonging to the same subcell does not take place until each orbital belonging to that subcell has got one electron. And according to Hund's rule, half filled or completely filled subcell is preferred configuration, preferred electronic configuration. Okay. Now, how to write electronic configuration of an atom? So during writing electronic configuration, you have to follow this rule, Hund's rule, Pauli exclusion principle, above principle. Okay, and there are two type of orientation of writing, two type of notation of writing electronic configuration of an atom. One is SPDF notation, another is orbital diagram. For example, hydrogen, electronic configuration of hydrogen atom. Hydrogen has only one electron, so electronic configuration will be 1s1. For helium, electronic configuration will be helium has 2 electrons, so electronic configuration of helium will be 1s2. For lithium, electronic configuration, lithium has 3 electrons, so in first orbital you have to give 2 electrons in s orbital, and in 2s orbital 1 electron. Okay, first you have to write the orbitals, symbol of orbitals according to increasing order. Okay, beryllium, boron, beryllium has 4 electrons, so electronic configuration of beryllium will be 1s2, 2s2. Okay, 4 electrons. Similarly, electronic configuration of boron, boron means 5, So in 1s orbital 2 electron, in 2s orbital 2 electron, in 2p orbital 1 electron, total 5 electron. So you have to arrange the electron according to Hund's rule, Pauli exclusion principle and Aufbau principle. You have to follow this principle during writing electronic configuration. Okay, and you can write the electronic configuration like this using orbital diagram. For example, carbon has atomic number 6, so electronic configuration of carbon is 1s2 2s2, so 4 electron is completed and 2 more electron left, so 2s2 2p2. So you have to write like this: 1s2, in 1s orbital 2 electron, in 2s orbital 2 electron, and in 2p orbital, and 2p subshell has 3 2p orbital, px py pz. So 2p orbital, in 2p orbital, in px and py orbital you have to give 2 electrons. So this is the electronic configuration of carbon. Okay, an electronic configuration of different element given here, you can check from this PDF or you can also read from your book also. Okay, very important how to write electronic configuration. You have to follow the energy order first. Okay, and one more thing, and here energy order of different orbital is showing, and you can see that energy of 3d orbital is more than 4s orbital energy. So first electron, after completing 3p orbitals, then electron will enter into the 4s orbitals, because energy of 4s orbital is less than 3d orbital, and after filling 4s orbitals, then electron will enter into 3d orbitals. Okay, for example, in case of scandium, titanium, or in case of iron, iron has atomic number 26. So in iron there are total 26 electron. So how to write electronic configuration of iron? You have to arrange total 26 electron in different orbitals. So in 1s orbital 2 electron, in 2s orbital 2 electron, in 2p orbital 6 electron, in 3s orbital 2 electron, and in 3p orbital 6 electrons. So 1s2 2s2 2p 16, and 3s2 3p 6 18, and then after 3p electron will enter into 4s orbital, then 3d. Okay, then first electron will enter into 4s orbital, 2 electron in 4s orbital, then in 3d orbitals. Okay, so 3d 6, and up to this, up to 3p6, it is the electronic configuration of argon. So you can also write electronic configuration of Fe like this: argon up to 18, it is argon, then 4s2 3d6. Okay, so electronic configuration of different element are given here, you can check. And some exceptional cases, exceptional electronic configuration are also given, and which are highlighted here. Electronic configuration of chromium, electronic configuration of copper. These chromium and copper has exceptional electronic configuration. Okay, it is given here, you can see. And electronic configuration of some ions also given here, electronic configuration of some ions. For example, suppose electronic configuration of Cl minus. You know Cl has atomic number 17, chlorine has atomic number 17. So electronic configuration of chlorine is 1s2 2s2 2p 6 3s2 3p 5. This is the electronic configuration of chlorine. Okay, and chlorine Cl minus has 17 proton but 18 electron. So electronic configuration of Cl minus will be 1s2 2s2 2p6 3s2 and 3p6. Okay, so how to write electronic configuration, I think you understood, and you have to practice of writing electronic configuration of different atoms and different ions. Okay, thank you students.